welcome everybody. This is the second lecture. In this lecture, we will talk about deterministic finite automaton. We will give the formal definition and we will talk more about its properties. So, the first thing that we will define is alphabet. So, an alphabet is a finite set of symbols. So, this is usually denoted by the symbols capital sigma or capital gamma. So it is a finite set containing symbols. So a very common example is the binary alphabet consisting of two symbols, let's say 0 and 1. Okay, or you can have more than two symbols and so on. A string over an alphabet is a sequence of symbols from the alphabet. Okay. For example, if you look at the binary alphabet consisting of the symbols 0 and 1, we have a string, let's say W, which is equal to 0, 1, 1, 0, 1. Okay. This is an example. Length of a string is the number of symbols in the string. Okay. So this is for a string, let's say W, we denote its length as W with a modulus sign around it. For example, the length of the string 0, 1, 1, 0, 1 is 5. It has 5 symbols in it. Okay. So we also have a special type of string called the empty string, or which is denoted as epsilon. So the empty string is the string consisting of 0 symbols. Okay, so this is denoted as a small epsilon. Okay. So the point to be noted here is that this string epsilon does not have any symbol. Okay. So this is not the same as the symbol 0. Okay. So here this is a string which has 0 symbols in it, and it is denoted using this character epsilon. So now given an alphabet sigma, we define the set sigma to the power I as the set of all strings W such that so W is a string over sigma and the length of W is equal to I. Okay. So, for example, if we take sigma as the alphabet consisting of symbols 0 and 1, then sigma square will be set of strings 0 0, 0 1, 1 0 and 1 1. Okay. So, these are the only 4 strings which have length equal to 2. So, now sigma star is the set of all possible strings that can be constructed over the alphabet sigma. Okay. So, this is written as union over all I greater than or equal to 0 of sigma raised to the power I. Okay. So, it contains sigma 0, sigma 1, sigma 2 and so on. So, an important point that must be noted here is that, so what is sigma 0? Okay, so, what are the strings that have length 0? Okay, so, sigma 0 is the set consisting of only the string epsilon, okay, because as we defined, epsilon is the string, the only string which has length 0. And although the following notation is usually defined, but it is very sparsely used. So, sigma plus is the set of all strings that have length strictly greater than 0. Okay. So, now we can define what is a language. So, a language L over an alphabet sigma is a subset of sigma star. Okay. So, language is basically any collection of strings from sigma star. Okay. So, in particular note that it can be the entire set sigma star as well, or it can be the empty set, or it can be any other set in between the empty set and the complete set sigma star. Okay. So, these are some of the basic notations that we will be constantly using and will be referring to for the rest of this course. So, now that we have this framework, let us get back to what we mean by deterministic finite automata. So, last time we gave an informal description of what a deterministic finite automata is, what a finite automaton is, and what kind of sets or what kind of languages such computational models are able to accept. So, today we will give a formal definition of the following. So, once again, before we give a formal definition, let us look at an example. Okay. So, consider the language L, which consists of all strings of the form W such that W has W ends with a 1. Okay. So, all strings that end with a 1. So how can we give a finite automata that accepts all strings that are in this language? Okay. So we will construct an automata that will have two states. So this two states will intuitively contain the following information. So one state will contain the information of all those strings that end with a 0, and the other state will correspond to all those strings that end with a 1. So here we have a start state. So we refer to the start state with the arrow pointing to it. So this is the state that will correspond to all strings that end with a 0. So whenever we see if we are sitting at this state and we see a 0, we remain at this state, and we will have another state that corresponds to all strings that end with a 1. So let's give them some names as well. So we'll call this state as Q0 and we'll call this state as Q1. So from Q0, if we see a 1, we go to Q1. Now when we are at Q1 and if we again see a 1, it means that the string is has a 1 at the end, which means that we will stay at the state Q1 itself. On the other hand, from Q1, if we see a 0, we will come back to Q0, because that means that now the last symbol of the string that we have seen is a 0, hence we should be at Q0. And now what are the strings that needs to be accepted? So according to the language L, we should accept all strings that end with a 1. So our accept state would be the state Q1. Okay, so we denote our accept state with a double circle. Okay, so that is the notation that we will follow. So now that we have this example, we will formally define what we mean by a deterministic finite automaton. A deterministic finite automaton, or which we will in short refer to as a DFA, in short DFA, is a 5 tuple Q sigma delta Q naught comma F, where okay, so before I proceed and I explain what each of these symbols mean, let us intuitively try to understand what exactly are we trying to quantify here. So if I get back to this example, okay, so coming back to this example that I gave, so a deterministic finite automata is basically a computational model that needs to capture whatever is happening here. Okay, so it needs to capture the structure of this object, this mathematical object. And if you look at this mathematical object, this is in some sense it looks like a directed graph. Okay, so you can imagine these states as vertices, and you can imagine these transitions that are happening as directed edges. So it is a directed graph which in addition has labels on the edges. So each edge has a fixed label, and in addition we have a specific state which is a start state, and we have some states which are our accept states. Okay, so this is what we need to quantify in our definition of a DFA. So that is what we are going to do here. So where capital Q is a finite set of states, sigma is the alphabet. This small delta is what is known as the transition function. So delta is the, let me just write it over here. So delta, which is a map from Q cross sigma to Q, is the transition function. Q naught, which is an element of Q, so it is a special state, is the start state, and F is a set of is a subset of Q, is the set of accept states. Okay. So now observe that once we have such a description, it exactly quantifies what the example that we gave earlier, that of a deterministic finite automata. So again, so if you, let's go over it. So Q represents the states that we have. So in this directed graph, it is the set of vertices that are there. Sigma is the alphabet. Okay, so these are the labels that we have on the edges of our DFA. So in this case, in the example that we had earlier, the 0 and 1. Delta is the transition function. So this kind of describes so this describes what the edges are going to be and what are the labels on these, on each of these edges. So what delta takes as input is a pair, is a tuple consisting of a state and an input symbol, and it goes to another state. Okay. So in the earlier example, so let's look at this example. So suppose if I give the state Q0 and I give the symbol 1, then it maps Q0 comma 1 to the state Q1. If I give the state Q0 and the symbol 0, then it maps Q0 comma 0 to the state Q0. Similarly, if I give Q1 comma 0, it maps Q1 comma 0 to the state Q0, and so on. Okay. So that is our transition. So this is the transition function. So for every pair, of consisting of a state and an input symbol, it produces a state that the automata goes to. Then we have a unique state Q0, which is our start state, and we have a subset of states which are the accept state. So at the end of reading the entire input, if the automaton is in one of the accept state, we accept that input, and if at the end of reading the input the automaton is in a state which is not an accept state, then we do not accept that input. So now let us introduce some notation related to DFA. So we say that a DFA M accepts a string W if so let's give an informal description for the time being. So if starting at the state Q0, the DFA ends at an accept state on reading the string W. Okay. So if starting from the state Q0, so we say that this DFA accepts a string W if starting at Q0 on reading the string W, the DFA ends at an accept state. Okay. And if it doesn't end at an accept state, then we say that it does not accept the string W. So now we can define language. So the DFA M accepts a language L subset of sigma star if every string in L is accepted by M and no more. Okay. So this is an important point. So we say that an automata, a finite automata M accepts a certain language L if every string that is present in the language is accepted by M and every string that is not present in the language is not accepted by M. Okay, so every string that is presented is accepted by M and no more, so no other strings. Okay, so it accepts exactly those strings that are in the language L. So this is denoted as L of M. So when we say L of M, we mean the set of all strings that are accepted by a DFA M. So again, as I said that this is a common mistake that people tend to make when they say that L is accepted by M is they construct an automata which possibly accepts every string that is in L and also some more strings, but that should not be the case. So when we say that an automata accepts a language L, then it should accept exactly those strings that are in the language L and no more. So some texts also use the term recognizes in place of accepts. So let me just mention that. So this is also referred to as M recognizes the languages. So as far as theory of computation is concerned, we use both these terms, accepts and recognizes, synonymously. So okay, thank you.